In our acoustic counter-detection risk management evolutionary machine learning project, we are applying machine learning to the problem of searching for a threat submarine while mitigating the effects of the threat submarine counter-detecting our friendly assets. This is a multi-objective optimization problem in which you don't get a single solution, but you get what's known as a Pareto optimal frontier of non-dominated plans. And so each point on that plan cannot be improved in one of its parameters while staying as good as it was in the others. You can see two of these curves in the graph on the slide, where you're looking at the cumulative detection probability, CDP, against threat submarines versus the cumulative counter-detection probability against friendly USW assets. And you can see that as you increase the CDP of a particular search mission, then you tend to increase your probability of being counter-detected as well. And the object of ACDRM is to present to the operator, planner, commander the options that they have available in terms of their plan. In particular, you're looking for inflection points that show sort of particularly good operating areas. So, for example, in this case, you see that if you have the threat diesel, you come to a point where all of a sudden it slopes up, which means you're at an area where you're increasing your cumulative detection probability in the threat without increasing the counter detection probability very much. And so it might be good to operate in that area there because you get, a higher, if you're willing to, sort of accept that amount of counter detection at all, then, then there's a big trade-off in terms of, operating toward the upper right in terms of getting better mission effectiveness without giving up much in terms of counter detection. This also shows you, what you can do if you really want to minimize counter detection. So the best you can do is along the y-axis there, where you basically have a zero counter detection probability, but a non-zero probability of detecting the threat. Or what you want to do is really detect the threat as quickly as possible. Then you can see those points, sort of on the far right of each curve, and you can see what your counter detection probability is. So that the idea of this is not like, sort of the traditional optimization systems we've been using to come up with an answer. It's to come up with a set of potential plans that the planner can then choose from depending on, particular commander's intent in terms of, how effective does the search have to be, and, how sort of bad is it from the point of view of the planner to be counter detected. Wagner Associates has been working in operations research, mathematics, and software development for over 59 years, primarily developing innovative algorithms and software for Department of Defense clients, and in particular, solving challenging and difficult Navy problems. We've been particularly successful in transitioning SBIR projects into programs of record. Some examples of that in the mission planning and threat mitigation area, which is where ACDRM lives, are MOKI, our mission optimization configuration item, which is in the Undersea Warfare Decision Support System, USWDSS. It passed APAVAL as part of Build 2, Release 3 in 2013, and we're currently upgrading it for Build 3 of USWDSS to handle both the strike level planning that it was originally designed for and also theater level planning. Another major project in the fleet is our acoustic mission planner, AMP, which is on all of the Navies and most of the export MH-60 Romeos, which is the ASW helicopter for the Navy and for many of our allies. We started work on that in 1999. We got through APABAL in 2005, and we've continued to enhance it and, have, for example, now can optimize not only a single helicopter, but also the operations of 4 helicopters at once. And it optimizes both the dipping sonar placement as well as sonobuoy placement. Some other systems that we've transitioned are a submarine route planner to minimize mine risk, and environmental data fusion and search effectiveness evaluation and optimization modules that have been integrated into MineNet Tactical, otherwise also known as METAL, which is the Navy's primary planning system for mine warfare. In the area of tracking and data fusion, we have a platform and cross-platform data fusion system integrated into USWDSS that also passed APABAL in 2013. We had multi-hypothesis data fusion engines installed on more than 10 different types of uncrewed surface vehicles. And these were also used in a series of ONR uncrewed surface vehicle swarm demonstrations starting in 2014 and ending in 2020 that were very successful at maintaining a fused common operational picture across, up to 5 USVs. In addition, we did a torpedo defense data fusion classification and alerting algorithm that associated all the relevant data to torpedo detection, fused it, and then estimated the probability that that track was an incoming torpedo. I'm Dr. Reynolds-Monick. I worked on all of these projects and have experience in designing, developing, and evaluating both target localization and mission planning and search optimization algorithms. The principal Navy challenge that we're addressing in this project is the large number of stealthy and capable near-peer threat submarines that we now are facing. In order to deal with this threat, we need to mitigate the threat counter-detection capabilities as much as possible when we're operating friendly assets in their vicinity. The initial transition will be into Undersea Warfare Decision Support System, USWDSS, to increase its capability by accounting for the counter detection and improving its estimate of mission effectiveness, as well as its improving the optimal solutions it generates. It's a complex problem, but the evolution of machine learning works very well in terms of constructing the Pareto optimal frontiers we need in order to give the planners a view of what the trade-offs are and allow them to pick the plan that best meets commander's intent. As I said in the last slide, our main threat is these modern, stealthy, and capable threat ASW capabilities. And therefore, the need for improving the planning tools in USWDSS so that they can mitigate threat counter detection capabilities when our friendly assets are searching, screening, or maintaining a barrier, and to do this with or without acoustic advantage. So in some cases, for example, if we're operating a submarine, we probably have an acoustic advantage because we're probably quieter than the threat. But in other cases where we're doing an active sonar search, we're definitely not. And so ACDRM is designed to provide, optimal solutions in both cases. In addition, if you're trying to covertly transit or covertly patrol, ACDRM will give you the best areas and the best routes in order to stay covert. Other programs that could benefit are the USWDSS FMS sales, as well as CBTSC, which is also part of IWS 5E, which is the program manager for USWDSS. The DDGs, CGs, and FFGs, which will get a version of USWDSS to support mission planning, and in particular the the new FFG, is being built to use such a system. But I expect that once we develop that, it'll probably be put into the DDGs and CGs through the ACB program. PEO subs could use it in terms of both planning covert transits and patrols, but also, search operations that minimize the probability of our submarine being detected before it detects the enemy. And then also, it could be used in the acoustic mission planner on the MH-60 Romeo to account for the fact that the threat submarines will definitely detect a dipping sonar. And so, how might you modify your plans to keep them optimal and assuming that the threat, reacts very intelligently to your operation. This slide shows how ACDRM can generate optimized mission plans that account for target counter detection, and basically the value of those plans, how much you can increase performance if you use this approach rather than the current approach of assuming that the target doesn't react to your search. So the key points of this are in the table where we look at 4 cumulative detection probability values. So on the columns, the first column, we generate target motion, assuming that the target evades intelligently. In the second column, we have a non-evasive target, which is what all the current systems use. And then in the rows, the top row, we optimize assuming that the target will evade, and in the bottom row, we optimize assuming the target does not evade. Okay, so the 2 key points here, I think. One is that if the target evades and we optimize assuming that the target doesn't evade, then in this particular problem, you'd only have a 28% probability of detection, which is the red value in the lower left. However, if you use an optimizer that assumes that the target evades, then you can come up with a plan that is 53% effective, so almost twice as good. So, there's a huge advantage in modeling the target as evasive. Now, the obvious question is, well, what if the target doesn't evade? How much are you giving up? Okay, so in this case, if you go to the yellow in the upper right, if you assume the target evades and the target does not evade, your plan gets an 81% probability of detection. If you assume it doesn't evade when you optimize and it doesn't evade, then you get 91%. So as should happen, if the algorithms are correct, you do better against a non-evasive target, assuming it doesn't evade. However, you don't do that much better. And so in this case, and in many others we've looked at, assuming that the target will evade and planning accordingly, basically gives you the best plan if the target evades, and a plan that if the target doesn't evade is just about as good. So I think you would always want to assume an evasive target unless you were positive that the target could not detect you. The figure in the upper right shows the result of doing this search planning. So in this case, we are assuming that the target is somewhere in that rectangle. We have 2 search tracks that you can see, both starting in the upper left and going down. One gets down and sort of hooks right, and the other one hooks left. And this is a picture showing basically assuming that we do not detect the target, we apply what we call negative information from non-detection of the target, and then generate a posterior probability map that accounts for the initial target location, target motion over time, and the fact that the search did not detect the target. And so, we would generate such plans, and like I said, we would generate them assuming that the target will evade, I think, in general, because you are not losing much if he doesn't. And also, of course, this gives you a much better estimate of your true effectiveness, because assuming that the target has the possibility to counter detect you and reacts accordingly, then our current systems, we would be thinking we were getting, 91%, but in fact, we were getting 28%. So that's a huge difference. And so this will give you not only a better optimized plan, but also a more accurate estimate of your true search effectiveness against an intelligent target. So our current status is we've developed our concept of employment. We've built our evasion models for the targets. We can optimize our search routes that account for target evasion, which I showed previously. We also have algorithms to minimize the probability of counter detection when friendly submarines are transiting covertly and when they're patrolling covertly. And we've looked at operationally relevant scenarios. We've put together our prototype, and we'll be looking for external evaluation by the Navy, and then we will eventually integrate it into USWDSS and other Navy mission execution systems. The three key features, advantages, benefits of ACDRM are the automatic recommendation of more efficient and effective use of limited friendly USW search assets that, by accounting for the fact that the threat element submarines have the ability to counterattack, innovate, or attack friendly assets, to automatically recommend routes for covert transits by friendly submarines, and to automatically recommend optimal patrol areas for covert operations by friendly submarines. Our initial transition path is very straightforward, which is to go into USWDSS to basically expand its current capability for evaluation and optimization to include intelligent threats that can counterattack friendly assets and can come up with plans to avoid being detected that ACDRM is able to mitigate with a more intelligent search design. Our current sponsor is IWS-5, and they would also sponsor the transition. As I mentioned before, the additional transition paths would be the USWDSS FMS sales, CBTSC, which handles the ASW planning on carriers, FFGs, followed by DDGs and CGs through ACB, PEO sub through APB, and the MH60 Romeo acoustic mission planner. We'd be interested in further conversations of technical details and integration requirements in any application you might have. So obviously, any kind of undersea warfare application has to deal with these issues, and we would certainly like to work with you in terms of both incorporating our evasive motion models, as well as our evaluation algorithms and our optimization algorithms, and also would be interested in any other multi-objective optimization problems where you are, not just trying to optimize a single value, but you are trying to look at multiple factors, all of which you'd like to, optimize, but clearly you can't do them all at once. So you need to construct a Pareto optimal frontier for your problem, and then have an efficient way to generate it. So since almost all real world problems are multi-objective in one sense or another, then you can do better using this multi-objective optimization approach than just going for optimizing a single value. And we have developed software that can efficiently do that, and we are interested in applying that in any case where it can make a difference in terms of operational performance.